Hello friends, welcome to this series on statistical mechanics. Today we will discuss a relation between statistical mechanics and thermodynamics. In the previous episode, we have discussed the evolution of statistical mechanics, and we discussed that how the thermodynamics evolved into a larger field within physics, which we termed as the statistical mechanics. So therefore, it is important for us to make a appropriate mathematical relation between thermodynamics and the statistical mechanics. So again, this relation was also formally proposed by none other but Boltzmann. Here, to make the relation, we can consider two boxes. Imagine that I fill an ideal gas in both these boxes. I name these boxes as A1 and A2. Here the walls which are separating these two boxes, I consider them to be impermeable, which means that the number of particles will be constant throughout our experiment, N1, N2. And also the second condition is that this wall separating these two boxes are fixed. It is rigid and it is fixed, which means that I can always fix a volume V1 and V2. So the walls are immovable, and therefore I fix a volume V1 and V2. But between the boxes, I allow temperature to exchange, which means that these two boxes will try to achieve a equilibrium temperature. Right? Which means what? Which means that the parameter which is connected to the temperature, which is the energy, will be different in both these boxes. One should note that at some equilibrium condition, which means that when these two boxes will exchange temperature and when it reaches an equilibrium, it will always reach to an equilibrium energy E1 equal to E1 bar and E2 equal to E2 bar. So these are the conditions in which this box will work. Now, in the previous episode, we talked about the importance of the total number of microstates, and we denoted denoted that number by omega. So here in this case also, let's imagine that the box A1, I represent the number of particles or the number of microstates by omega 1 E1, and for the box A2 I represent it by omega 2 E2. As I told you in the previous episode, of course it would be more prompt to denote omega 1 as omega 1 of N1 V1 E1 and omega 2 as N2 V2 E2, but since the energy is the only parameter which is allowed to change in this experiment, we just limit ourselves to writing omega 1 E1 and omega 2 E2. Those are the previous conditions for this experiment. Now, for this box, for this combined box system, which means that you have the A1 and the A2, imagine that I consider a sum of states system, which I denote it by, say, A0. So for the A0, I can write the statistical probability or the number of microstates omega as omega 0 E1 E2, right, which means that omega 0 is the sum of states in the when we consider both the systems together, and this omega 0 can be expressed in terms of omega 1 and omega 2. How does this relation comes from? This basically comes from one of the expressions which you might have studied in your statistics course, which means that if there are two processes A1 and A2 which are independent processes, and its probabilities are, say, P of A1 A2, let me write it down for you. The probability is P of A1 A2 can be written as P of A1 into P of A2. So this is a fundamental relation which comes from the statistics. So our experimental situation over here is quite similar to the situation here, and therefore omega 0 E1 E2 is equal to omega 1 E1 into omega 2 E2. Now for my mathematical convenience, let me express this part of the expression in terms of E1. So how will I do that? I can write down that as omega 1 E1 into omega of E0 minus E1. Why? Because I have two boxes which are having energy E1 and E2. But one of the condition for this combined system is that these boxes or this wall separating them do allow the temperature to exchange. But for the combined system, it does not allow any temperature exchange from outside this combined box system, which means that among these two boxes the energy will be always constant, which I can write it as E0 equal to E1 plus E2. Since it does not allow the exchange of energy from outside, I can write down this as a constant. So naturally this E2 can be expressed in terms of E1 as E0 minus E1. So that is the idea by which I change this expression into this one. Now what will I do? Now I allow the system to achieve the desired equilibrium, which I talked in the beginning of this episode. So if I allow the system to achieve equilibrium, so on equilibrium we know that at a condition in which we get the equilibrium, we can always try to consider a minima and carry out the differentiation, and therefore the left hand side of that expression can be considered to be 0. So let me try to invoke that mathematical convenience over here by differentiating with E1. At the same time, I should tell you that it is equivalent to have the differentiation being carried out with E2 also, but here we will carry out the differentiation with in terms of E1. So therefore dou of omega 0 E1 E2 by dou of E1 is equal to dou of omega 1 E1 divided by dou E1 into omega 2 E2. So here we are going to apply the product rule. So the first term dou of omega 1 E1 divided by dou of omega 1 by dou E1 into omega 2 E2 plus omega 1 E1 into, here we are supposed to be differentiating this omega 2 E2 in terms of E1, but again for my mathematical convenience I am going to differentiate in terms of E2, which I will come back in a minute and explain to you how can we manage such a situation. So I differentiated it with dou E2, but in order to make the make it mathematically accurate, what I do is that I add this expression there. So that these two terms will get cancelled, and so that effectively I will be differentiating in terms of E1. So, this is it. So, I applied the product rule, fundamentally I differentiated in terms of E1 and I reached this expression. So, here we have carried out the differentiation in terms of E1 and applied the product rule. So, now the question is that what is the kind of expression which how can we simplify this dou E2 by dou E1. For that purpose, in the previous slide we have written E0 is equal to E1 plus E2, which was a constant, which means that if I take the differentiation in terms of E1, for example, in this expression dou E0 by dou E1, which will give me dou E1 by dou E1, which will be 1 plus dou E2 by dou E1. The left hand side here will give me 0, right, because this is a constant value, and we are trying assuming that we are differentiating in the minimum or the minima condition. So, the dou E2 by dou E1 based on this expression I can write it as dou E2 by dou E1 is equal to minus 1, right. So, here in this equation I can substitute dou E2 by dou E1 by minus 1, and also the left hand side here will be again can be considered to be 0, because this is again a constant value, right, or we are differentiating in a minima condition. Incorporating this condition for the left hand side, we can write down the expression as 0 is equal to dou of omega 1 E1 divided by dou E1 into omega 2 E2, and the second condition was dou E2 by dou E1 is equal to minus 1. So, we incorporate that also, minus omega 1 E1 into dou of omega 2 E2 divided by dou E2. So, we have incorporated both those conditions and we reached here, and now we will rearrange this expression by bringing the bringing one of the terms here to the other side. So, on rearranging I can write it as 1 by omega 1 E1 into dou of omega 1 E1 divided by dou E1 is equal to 1 by omega 2 E2 into dou of omega 2 E2 divided by dou E2. So, what I have done is that I have just rearranged this expression, rearranged it into two sides of the expression. So, now this sounds like the derivation and the differentiation of one of the famous quantities. What is that? This actually is indicating the differentiation of a logarithm. So, we will incorporate that idea into this expression now, which I can write it as dou of ln omega E1 divided by dou of E1 is equal to dou of ln omega E2 divided by dou of E2. You can always note that we are carrying out this differentiation in the limit E1 equal to E1 bar, because if you remember I told you about the equilibrium condition as the energy always reach an equilibrium state of E1 bar and E2 bar on equilibrium conditions. So, this is the expression dou of ln omega E1 by dou E1 in the limit E1 equal to E1 bar is equal to dou of ln omega E2 by dou Et in the limit E2 equal to E2 bar. Now, from your previous courses you might be knowing that whenever sees this kind of an expression, I can always bring up a new constant or a new physical quantity and define them and make them equivalents. For here let me put a notation of beta. Beta. So, beta I define it as dou of ln omega by dou E. If I write it write the full set of macroscopic quantities, which is n, v and the E. So, beta I define it as dou of ln omega by dou E, and in that condition this expression I can write it as beta 1 is equal to beta 2. So, beta 1 is equal to beta 2 at what condition? At an equilibrium condition, right. What is that? How will you define that equilibrium? This equilibrium, if I go back and think about it, this equilibrium I achieved by doing an experiment in which I allowed the temperature to exchange, which means that the beta 1 is equal to beta 2 will give me, or this condition is valid at the thermal equilibrium. Which means that if I take a statistical system and I allow the system to achieve thermal equilibrium, the condition which that system should obey is that beta 1 is equal to beta 2, where beta is equal to dou ln omega by dou E. Okay, so that is one thing which you should take into consideration for your further course. Now, our original idea was not to derive this condition for thermal equilibrium. The aim was to make a relation between the thermodynamics and the statistical quantities. For that purpose, I will utilize the famous thermodynamical relation which was originally proposed by Maxwell. dE is equal to T ds minus P dV plus mu dN. So, this is the famous thermodynamical relation. D is equal, where E is the energy, T is the temperature, S is the entropy, P is the pressure, V is the volume, mu is the chemical potential, and V is and the N is the number of particles. Chemical potential might be a new term for you, which I will tell in a short while in this episode or in the next episode, because it needs a separate explanation. So, for the time being, consider this as chemical potential. So, in our experiment, we if you remember, we started by assuming two boxes A1 and A2, and the condition was that the walls were immovable and impermeable, which means that the dV is equal to 0, dN is equal to 0, which means that I can now in this situation, in the case of thermal equilibrium, I can write it as dE is equal to T ds. All the other terms will become 0. So, d is equal to T ds, and now I have I know one expression for the for the S, which I write it as which if I put that now is equal to 1 by beta dou ln omega, rather I will use d. So, d is equal to 1 by beta d ln omega, which means that I can write T ds is equal to 1 by beta d of ln omega, right. Which means that this expression I can write now it as ds by d ln omega is equal to 1 by beta t. ds by d ln omega is equal to 1 by beta t. So, this expression is where Boltzmann made its major proposition. What was that? He considered this quantity as a constant. And this constant we otherwise call it as Boltzmann's constant K. But this constant was his contribution, because there is no way we could assume that this expression should be ds by d ln omega cannot be considered constant before Boltzmann, but he proposed that as a constant. Ds by d ln omega is equal to a constant. So, therefore, based on this expression I can write it as S is equal to K ln omega. So, this is the relationship between the statistical mechanics and the thermodynamics. Why? Because the omega is a statistical quantity, whereas S is a thermodynamical quantity. All the thermodynamical quantities, you know that you can measure it, you can observe it. So, the entropy, which is a thermodynamic quantity, is now being connected to omega, which is totally a statistical quantity. What is omega? Omega is the thermodynamical probability or the total number of microstates, which is totally a statistical construct. So, therefore, this relation connects between the entropy and omega, or the thermodynamics and the statistical mechanics. So, basically with this expression we have made a connection between the thermodynamics and the statistical mechanics. So, we will end this episode here. In this episode we have discussed or we have derived a relation between the statistical mechanics and the thermodynamics by using two boxes which has a peculiar kind of walls. Now, we need to see in the next episode the significance of this expression, and also what are the other kinds of possibilities in which microstates and macrostates can be managed. Thank you.